nuclear magnetic resonance, that is NMR spectroscopy. First of all, to start with this topic of NMR spectroscopy, we need to have an idea about the properties of nuclei. So not going to the very detailed explanation in the properties of nuclei, I have listed down here some of them in a very brief way. Let us see what are they. Spinning nucleus only give NMR. For a nucleus to be NMR active, there should be non-zero spin number for the nucleus. Spin number of nucleus is the sum of unpaired nucleon spin number. What does this mean? That is, the nucleons like proton half spin, neutrons half spin, they sum up to form the nuclear spin number. Let us see how they sum up to form using this table. Here, if you see very carefully, proton number, neutron number and nuclear spin. If we set both this number of proton and the number of neutron as even, then we will get to see the nuclear spin as 0. If we set one odd, another even, then we will get to see it is not equals to 0. If one is even, another is odd, then we will get to see as it is not equals to 0. Rather, we are getting, in case of one odd and one even, we are getting half, 3 by 2, 5 by 2 in a fractional form. Now, at last, if we set both of them as odd number, then we will get to see it is not equals to 0, which is equals to 1, 2, 3, 4 like that. Now let us see what does this nuclear spin is to do with NMR spectroscopy. If nuclear spin I is equals to 0, then it is magnetic nuclei. If nuclear spin I is not equals to 0, then it is non-magnetic nuclei. And magnetic nuclei is the only one which gives NMR spectroscopy. The things to be remembered. Now if we see here in our table, in the second row, one odd, one even, if we swipe them even odd, we are getting fractional form half, 3 by 2, 5 by 2 as a I. So these all are magnetic nuclei. The magnetic nuclei, when we consider this magnetic nuclei, I is equals to half, then it is called spherical nuclei, or it is called non-quadrupolar nuclei. And if it is I greater than half, like 3 by 2, 5 by 2, then it is non-spherical, or we can say it is a quadrupolar nuclei. See, the spherical nuclei, it looks like this. We can imagine it as like this. When there is spin I is equals to half, then it is looking like this, spherical, or it is called non-quadrupolar. This is very, very important. We need to remember this. And if its I is equals to greater than half, then it is non-spherical nuclei. It is quadrupolar nuclei, and it may be looking like this. What I have imagined, you can imagine also like this. Now taken into consideration, when there is I is equals to 0, they will also have a spherical shape. Now taking into consideration, we have only I is equals to half, which is spherical nuclei. The spherical nuclei looks like this, where they have the properties. One is electrical, another is magnetic properties. Both of them are perpendicular to each other. I showed them it as like this with arrows. Electrical properties, it depends on the shape. Like spherical shape, it is dipolar. Similarly, the magnetic properties, dipolar, that is north pole, south pole, like that. If it is 4 pole, then it is quadrupolar. Likewise, electrical properties have 2 to the power n pole. That means non-spherical nuclei will have dipolar, magnetic and 2 to the power n electrical properties. That is 2 to the power n, in case of n is equals to 1, that is 2 dipolar, 2 to the power 2, 4 quadrupolar, 2 to the power 3, 8 octapolar, and goes on. only 2 to the power 2, that is 4. Quadrupolar property is important to affect the NMR spectrum. In case of spherical nuclei, NMR signal will be sharp due to high relaxation time. It looks like this, sharp signal. And in case of quadrupolar nuclei, due to their very low relaxation time, the signal will be brought as it is shown here like this. This is just an notion to denote the broad spectrum. So the quadrupolar movement of nucleus is responsible for the lowering of their relaxation time. As we have already encountered with the word relaxation time, now what this relaxation time really is? It is the time required for a nucleus to relax from the excited state to the ground state. And the relaxation time is the only parameter to explain the signal width in NMR spectrum. Now the relaxation time and the signal width in NMR are interrelated with uncertainty principle. Like in case of uncertainty principle, delta x into delta px is greater than or equal to s by 4 pi, that is constant. Similarly here, relaxation time delta t into signal width delta mu bar is equals to s by 4 pi. Using this correlation, if we increase here, if we increase the relaxation time, then signal width will get lowered. That means we'll get a sharp signal. So in case of half spin nuclei, due to sharp signal and easy to record in NMR spectrum, half spin nuclei are more popular compared to that more than that of half spin. So the half spin nuclei, we can see I have tabulated the half spin nuclei here. The half spin nuclei are of two types, that is concentrated nuclei and dilute nuclei. The concentrated nuclei is that which is having a high natural abundance, and that will remain with high effective concentration in the sample. And the dilute nuclei is that nuclei which will have a low natural abundance, that will have low effective concentration in the sample. So the concentrated nuclei, for example 1H 100%, around 100%, 103 rhodium, around 100% abundance is there, 31P 100%, 19F 100%. So these all are the selected data which we need to remember at most. And if we come here to the dilute nuclei, 13C 1.1%, around 15 and 0.37%, 29 SI, this is 5.9%, 19 SN, this is 1.16%. Now to understand this half spin concentrated and dilute nuclei, I have taken one example. In this, 1 gram of this sample is taken, where whole sample will be active for 1H NMR, that is proton NMR. Why? Because proton NMR, that is 1H is 100% NMR active. But in case of this 13C, only 1.1%, that means in 1 gram, 0.11 gram will be 13C NMR active. With this example, now we will proceed forward towards the basic concepts of NMR signal. As we can see here in this figure, south pole, north pole of the magnet, where two nucleus are placed in such a way that their spin energy are degenerate to each other. Now as soon as we put the external magnetic field, their degeneracy will break down, and the one which is opposing the external magnetic field will go to the higher energy level, and one which will be overlapping the external magnetic field will go to the lower energy level. So this will create a population difference due to this difference in energy level created by the external magnetic field. This can be correlated as the energy difference which is directly proportional to the applied external magnetic field, that is B naught, and this correlation can be imagined as that like delta P is the population difference which is directly proportional to the delta E. So with this two correlation we can have this idea as that delta P, that is population difference, will be directly proportional to B naught. We need to remember this relation. So in the presence of external magnetic field, that is B naught, proton starts precessional motion, that is proton will be at the precessional frequency, that is called gyroscopic motion. So the precessional frequency will be directly proportional to the external magnetic field. If we remove this proportionality constant, then we will come to another relation, that is precessional frequency will be equal to gamma B naught, that is gamma is the constant that is called gyromagnetic ratio of the nucleus. Precessional frequency will be equals to gamma into B naught. When we put B naught is equals to 1 Tesla, then precessional frequency will be equals to gyromagnetic ratio. So at constant magnetic field of 1 Tesla, the precessional frequency will be equals to the gyromagnetic ratio of the nucleus. That is, gyromagnetic ratio gamma is an inherent property of the nucleus. We can understand this more by taking an example of gyromagnetic ratio of hydrogen is equals to 42.57 MHz per Tesla. Gyromagnetic ratio of 13C is equals to 10.71 MHz per Tesla. Using the concept whatever we have studied over the precessional frequency, we have some problems to do. Calculate the precessional frequency of proton at 5 Tesla magnetic field. Since we know that precessional frequency is equals to gyromagnetic ratio into B naught. Here gyromagnetic ratio of proton we have 42.57 MHz per Tesla, and the magnetic field given here is 5 Tesla. So putting the value here, we will get 212.85 MHz. So the precessional frequency in Hertz we will get 212.85 into 10 to the power 6. Another problem we have, calculate the precessional frequency of magnetic nuclei if its gyromagnetic ratio is 1 into 10 to the power 8 per radian per Tesla in 10 Tesla magnetic field. So first of all, here we know the formula, precessional frequency is equals to gamma into B naught, but gamma we should convert it in the form of megahertz per Tesla. We have given it in the form of radians per Tesla, per radian per Tesla. So the gyromagnetic ratio gamma is equals to 1 into 10 to the power 8 by 2 into 3.14, that is 2 pi, is equals to 15.9 into 10 to the power 6 hertz per Tesla. So this we can convert it as gamma is equals to 15.9 megahertz per Tesla. Further, if we put this value of gyromagnetic ratio in the formula, we will get it as precessional frequency is equals to gamma into V naught. Gamma we have 15.9 megahertz per Tesla. So as we put the value 15.9 megahertz per Tesla into 10 Tesla, this Tesla will get cancelled with each other and we will get the value of precessional frequency as 159 megahertz. As we have solved some problems related to the precessional frequency, now let us move towards the nomenclature of the instrument. Nomenclature of NMR spectrometer always based on the precessional frequency of that. Say for example, 500 megahertz instrument means precessional frequency of TMS proton will be 500 megahertz. As we know, precessional frequency at 1 Tesla magnetic field will be its gyromagnetic ratio that we have discussed earlier. The gravimetric ratio now is composed of two nuclear parameters, that is gamma is equals to mu n into Gn. Mu n is nuclear Bohr magneton and Gn is nuclear G factor. With this relation, let us solve some problem which are asked in the previous year examinations. Here, the nuclear G factor of proton 1h and 14n are 5.6 and 0.40 respectively. If magnetic field in an NMR spectrometer is such that the proton resonates at 700 MHz, the 14n resonates at, we need to find out which of the following given answers is correct. Now, as we already know that precessional frequency is equals to gamma into V naught, and right now we have established the relation using two nuclear parameters, that gamma is equals to mu n into Gn. With this, if we put this gamma is equals to mu n into Gn in the above relation, we will get precessional frequency is equals to mu n, Gn and B naught. So this is the relation what we are going to use in this problem. Using this, let us assume that precessional frequency is equals to mu, say for example. Now we have gamma h by mu h by mu n is directly proportional to Gn h by Gn 14n. So this relation what we got here is from the above step. Now using the values whatever it is given in the question, as proton resonates at 700 MHz, that means we can put the value of this as 700 MHz, and 1h and 14n G factors are 5.6 and 0.40. We can put the value of nuclear G factor for proton as 5.6 and nuclear G factor for 14n as 0.40. So using all this value, we will get that the precessional frequency or the resonating frequency for 14n as 50 MHz, which is given in the option number D. Similarly, we can solve another problem which is given as like this. The G factor of 1h and the 13c are 5.6 and 1.4 respectively. For the same value of magnetic field strength, if 1h resonates at 600 MHz, the 13c would resonate at. So this problem is exactly as same to that of the above what we have solved. Using the same procedure, same steps, we can find out the answer of this question as 150 MHz. With this, I want you to give thumbs up right down below if you like my videos. Thank you.